Hacker Hotel. Welcome to the last day of Hacker Hotel. We'll do this talk in English. Interesting talk, Network Hacking 102. So please enjoy this talk and give it up for the speaker.
Yeah. Welcome everyone. Welcome all. This will be Network Hacking 102. I did a session Network Hacking 101 during the previous Hacker Hotel, and a special request of Dimitri. I came back with yet another talk about network protocols, network hacking, and how protocols work, how they should work, and what can be done to abuse these protocols. I want to stress out beforehand, it's for educational purposes only. If you abuse the knowledge you learn here, you're on your own. Let's see how long this takes. Well, the good news is this talk is scheduled for an hour, and I don't have enough material for that, but I wasn't hoping to fill it this way. Excellent. I want to talk to you about heroes. Well, not these clowns, of course, no. Real networking heroes. Who of you knows who these two people are? The one on the right, it was part of the pub quiz yesterday, so Edsger Dijkstra, he is obviously well known. But the lady on the left, anyone here are familiar with it? No? Well, excellent. The one on the right is Professor Edsger Dijkstra, inventor of the Dijkstra protocol, used in Dijkstra algorithm used in several networking protocols. And the lady on the left is Radia Perlman, inventor of spanning tree protocol. The reason I brought up these two persons is because spanning tree protocol and, for example, OSPF are two widely known and used networking protocols. They're open standards. A lot of vendors implement these. And I'm going to talk to you a bit about spanning tree protocol and the open shortest path first protocol. I will give a brief overview of these protocols, what they're designed to do, and how they work. This is not going to be an in-depth session because we need quite a lot of more time than 1 hour. But let's start with the basic scenario. You're on a campus with basic networking in place. The network uses open standards, spanning tree protocol, open shortest path first, and very basic configuration. What could possibly go wrong? A bit of history on spanning tree protocol. It's been around for quite a while, since 1990. It's a loop prevention protocol. What happens if an Ethernet frame gets sent and bounces around and around? The thing with Ethernet, it does not have a time to live or any other mechanism in place to make it die out after a while. It keeps on going. So that's why spanning tree protocol was invented. It's a loop prevention protocol. There are a number of standards that basically perform this function. There's the basic spanning tree protocol, there's the rapid spanning tree protocol, a number of standards. It works by building a tree. It elects a root bridge and then builds a tree without any loops that might cause Ethernet looping, broadcast storms, and all sorts of nasty things. The way it does this, it exchanges information. In the entire network, with switches, BPDUs, bridge protocol data units, are exchanged to make sure that every switch knows the best way to the root bridge and a single way to the root bridge. This is important to prevent the loops. A network port on a switch can have multiple roles and multiple names. There's the blocking, listening, learning, and forwarding. Let's start with blocking. If the spanning tree protocol detects a loop, it can place a port in blocking, which means it does not transmit any traffic. But if for some reason a link somewhere else fails, it can put the port in forwarding. So besides being a loop prevention protocol, it can also be used to create some form of link redundancy. When connecting a new switch, all ports start down in blocking. After a short while, and the time this is depends on the protocol, a full cycle with the original spanning tree protocol can take up to 50 seconds. When traveling to other implementation of spanning tree, for example, rapid spanning tree, it brings it down to about 6 seconds. So it's quite a lot faster convergence. It listens for BPDUs. It does not learn any MAC addresses of any connected host. It listens to BPDUs to determine what is going to be my root port, the shortest way to the root bridge. After a while, it goes to the learning step, which means it's still not going to forward traffic. It does learn about hosts in the VLAN, and if the topology allows, it's going to the forwarding state, which is actually actively going to forward traffic. Then there are a number of ports roles. The root port. A switch has only one root port, which is the port that's always in forwarding, which is the shortest way to the root bridge. A port can also be in designated state, which means it's going to be in the forwarding state, but it's not the shortest path through the root bridge. Then there's the blocking state, loop prevention. Later implementations add a few more roles, for example, alternate root port, which means it's in blocking. But if the primary root port goes down, that role takes over. This is quite a bit of boring slides, sorry about that, but I have some pictures which should make it all a bit more clear. First, let's go to basic connectivity. When we have Alice, who wants to talk with Bob, they're in the same subnet and a couple of switches are involved. Alice starts by sending an ARP. I want to send traffic to Bob. I have his IP address, but not his MAC address. So Alice will send a broadcast sourced by her own MAC address of the network interface card in her machine, which arrives at the first switch. What happens? The switch will learn the MAC address of Alice. It boots it down in its own MAC address table and says, this port on the left, I know that it's connected to host Alice with this MAC address. It then looks at the destination. It's a broadcast. It goes out of that link and travels to switch 2, which in turn does the same. It says, okay, I receive a packet that's been sourced by the MAC address of the machine of Alice. It learns the MAC address of the machine of Alice and puts it in its MAC address table. It's a broadcast, it sends it out over every port it has except the one on which it received the broadcast. So all other ports get the broadcast except the link to switch 1. It sends it out to Bob. Bob says, hey, this is my IP address, here is my MAC address. It sends an ARP reply. At the moment the machine of Bob sends the reply, switch 2 will learn the MAC address of the machine of Bob. It then knows, hey, this destination is, I know that, it's the machine of Alice. I know which port to send it out on. It sends it to switch 1. Switch 1 says, okay, this is destined for the machine of Alice. I know this destination, and sends it out of the port connected to the machine of Alice. Quite straightforward, but not very redundant. Thanks. What happens if we add another link? Alice sends out an ARP. Same scenario as last time. The switch then sends the broadcast out over the upper link to switch 2 and the lower link to switch 2. If you don't have spanning tree protocol, what will happen? Switch 2 will receive a broadcast packet. On the upper port, it sends it out on all other ports. So it sends it out to Bob, but also towards the lower port. The broadcast received on the lower port gets sent out to every connected port except the lower port. So that means to Bob again and to the upper port. In effect, one broadcast will keep running in this way, and one will keep running in this way. And that's only a single broadcast. There is relatively low traffic volume on broadcasts, but it does not die out. So if Alice connects to 3 other machines, there are 6 more packets running in here. And if, for example, Alice is going to be rebooted, it's going to forget about MAC addresses they learn and going to start all over again. The broadcast here, if the links are not disrupted, keep going, keep going, keep going, and you have a broadcast storm on your hand. That's nasty because it will saturate all the link, eat all CPU cycle on the switches, and basically going to crash your network. It's usually not desired. There are a few ways around this. One logical link. If you tell your switches there are 2 physical links, but they're going to act as a single logical link, if Alice is going to send a broadcast, switch 1 is going to forward it over either of these 2 links, but switch 2 will forward these links only over the side to Bob and not back over the other link because it treats it as a single logical link. If in this scenario spanning tree is activated, the first thing it will do is block one of the ports. For example, this one here, on switch 2, the bottom link. That will also prevent a broadcast storm or a loop, but you have only one usable link. And that's the same basic scenario as you had in this previous slide with just one link. So you add another cable and you get nothing in return. So adding, bundling these links into a single logical link is going to improve your bandwidth and your redundancy. Because if one of those 2 physical links fail, the logical link stays up. Now let's go to a basic network design. This is what they call a collapsed core. We have 2 core switches and 2 access switches. The core switches are interconnected and each access switch is connected to both core switches. I added the priorities for the root bridge and the backup root bridge. In spanning tree protocol, the lower value wins. So the upper left core switch, core 1, is going to be the root switch. In case something goes wrong with core switch, we want to have a little say in who gets the backup root bridge. So that's why the core switch 2 has a priority that's just a bit higher than the other one. It's generally not a good idea to have one of the access switches, which are basically usually quite small and not up to the task, to get these elected as a root bridge. Since the default priority is 32,000, there's little to no chance that the access switch will actually become a root bridge. Now, for the roles. This is the root bridge, and all ports going out of them are going to be in forwarding state. They're all going to be designated ports. Each other switch will have a root port, which is also going to be in forwarding state, which is the shortest path to the root bridge. And then a number of ports are going to be in blocking mode. Loop prevention again. Let me go to switch off my wireless. See if that'll solve things. In essence, this is what it looks like on the physical side. If you take away the block ports, this is what you end up with. No loops whatsoever. So that means if traffic is being sent from access switch 2 to access switch 1, they're all going to go through the root bridge. What happens if you add another switch? We have a very curious hacker here who is interested in traffic going through one of the access switches, usually towards the data center, towards the core switch. So it's going to plug in its own switch. Plug it into access switch 1, plug it into access switch 2. With an even lower priority, 0, the lowest value possible. Then this will become the new root switch. What happens? all traffic from access switch 2 towards the place where usually your routing is, in the core switches, is passing through the hacker switch, which means you can intercept traffic, you can manipulate traffic, you can listen in on everything, you can are the first one to inject all sorts of nasty things, man-in-the-middle attacks and stuff like that. So, if your target is on access switch 2, you're done. But since a hacker is only in control of its own switch and not the rest of the network, what happens if he was curious about traffic on access switch 1? How to solve that? Well, just add another switch. Make the route it was taking a bit less desirable than the previous scenario. It's still the new route bridge. All roles are distributed again, with the hacker switch as the new route bridge. And this will be the new topology. All traffic from access switch 1 towards the place where routing is on the core switches now traverses the hacker switch. So we did not change any configuration on the core switches and the access switches. We just added in 2 more switches. Something to think about. This does not matter what is on here, but the VLAN this device is in and the VLAN this device is in, all traffic now goes through here. There are a few mitigating measures possible. What to do if you manage the network, how to prevent this. The first is think about this in the design phase of your network. Implement multi-chassis Ethernet channel, which basically means I have 2 core switches, I have 2 links going down to each access switch. But I want to treat them as a logical link. Normally, port channels can only be done between 2 switches. That means 2 chassis switches. But there are some tricks to make an uplink of a single switch, 2 uplinks to 2 separate switches, act as a single switch. Multi-chassis Ethernet channel. There's also a technique called root guard. If you configure that on your network, if a switch receives a better BPDU from another switch that says, I want to become a root switch, it gets ignored. And another technology, 802.1x, which basically means everything that gets connected to my network has to be authenticated. That can mean a PC, a printer, an IP camera, or another switch. If it's not known, it's not going to be able to access your network. There are also a few alternatives. Spanning tree, as we just saw, is quite old and does not have the fastest convergence. 30 to 50 seconds is not uncommon. It still happens. So, a number of alternatives are thought up. Trill, transparent interconnect of lots of links. It's one of the successors of spanning tree protocol. It actually uses, under the hood, the Dijkstra algorithm as well. Shortest path bridging, another standard that's also being used as a successor of spanning tree. And VXLAN, an encapsulation technique which uses a routing layer to transport Ethernet traffic. One of my personal favorite, training. If you're going to be managing a network, you need proper training. Otherwise, you're going to make a lot of mistakes, which usually incur a lot of risks, a lot of impact, a lot of downtime. Training is really important to be able to make a proper design and to be able to troubleshoot a proper design. Another one, logging. All network devices in an enterprise environment are capable of sending multiple types of logging. It can be SNMP traps, it can be syslog. Send them all to a central collector and parse them whenever something happens. That's the best part, reading the logs. If you are sending all logs to a central repository but don't do a thing with it, you might as well not even be logging anything. And there's another nifty feature. port security BPDU guard, which basically means if you're expecting a host, a PC or a laptop or whatever connected to that particular switch port and not another switch, you configure BPDU guard, which basically means if another switch, for example our hacking switch, is connected to the network, it's going to send out BPDUs for the root bridge selection we talked about earlier. BPDU guard kicks in and blocks the port. It sets it's an error disabled, make sure there's manual intervention needed to prevent unauthorized switches being hooked up to the network. It's a rather effective way of preventing this particular attack. This is the spanning tree part of the presentation. Any questions so far? Is anyone awake still after the first part of the presentation? Excellent, excellent. Now for the second part of the presentation, OSPF, the Open Shortest Path First protocol. It's a routing protocol. The previous protocol was purely Ethernet frame based, and routing protocol is a bit higher on the OC model. It's about IP routing. It's an IGP, it's an interior gateway protocol, basically means you use it within a single domain. If you're responsible for a network, it's a single domain. It's a link state protocol, which means that every router in the domain knows about the entire network. So every router running OSPF is going to share its information about every single link it sees. Each router builds its own topology database and then calculates the best route to each route. There are a few official RFC requests for comments from the IETF that describe the standard in detail. Every single router knows about the entire area. After it gathers this information, it's going to run the shortest path first algorithm, or the Dijkstra algorithm, to make sure it actually elects the best route and adds these to routes to its routing table. The best part, it's a very scalable protocol. If you have 200 routers in a single domain, OSPF is more than capable of handling that. It's a loop-free environment. There's always a single best path. If that fails, the Dijkstra algorithm kicks in, it creates a new best path, and not a single time there's a loop. If you have two equal cost routes to a single destination, it even has equal cost load balancing implemented. And there's a reasonably fast convergence. If it sees an actual link going down, the Dijkstra algorithm kicks in at once. If not, it usually takes about 30 seconds. It's configurable, you can have it up to sub-second level, to detect a link failure and recalculates the area. This is all a bit boring and a lot of text. What does it mean in practice? Here's a handful of routers. What happens if I have a host connected to LAN A who wants to talk to a host connected to LAN B? What's the best route? Anyone? Is it going to be the upper route or the lower route? Anyone? What? The lower route? So from here it's 1, 2, 3 hops. From here it's 1, 2, 3, 4 hops. So the lower one looks best, right? Yeah. Yeah. But what if these links are very low bandwidth, and this is all gigabit network? Then I think the upper route looks a bit better. A protocol needs a way to determine the best route. For OSPF, it's called cost. You can configure the cost for each single link, but usually if you don't configure anything to influence it, it's going to use the bandwidth of the link to use as a cost for its calculations. Here's a nice one. What should happen? We have a router 2 here, which is connected to a server park with a very familiar IP address. It runs a DNS server. connected to router 1, which is connected to client networks. There's just a small network here in between, connecting router 1 to router 2, and the client access as this one, this subnet here. What should happen? Router 1 knows of the link to router 2 and the link to client's networks. It sends that information to router 2. Router 2 knows of its link to router 1 and the link to the server park, and it sends that information to router 1. So both routers know of all the networks here in the picture. So here it is, router 1, the left router, knows about the client LAN, the connection to router 2, and the server LAN. This one is directly connected, this one is directly connected, and this one is being learned through OSPF. Routing table for router 2. It knows about its directly connected link to router 1. It knows about its directly connected route to the server park. And it learned through OSPF the client network. Everything right so far, right? Everyone can configure OSPF. It's not that hard. Router OSPF 1. We add a router ID. It's optional. And we say network. Everything is going to belong to this area. This is all. This works. Trust me. It's a very basic configuration. Shove it in here and it'll work. Networking is not that hard. What could happen? A hacker adds its own router, connected to the client network, with also the 8888 IP address, but with a slightly smaller net mask. This is a 24-bit net mask, this is a 25-bit net mask. Which basically means that this network is half the size of that network. The hacker router also runs OSPF. What happens now? The hacker router will connect to router 1 using OSPF. They will exchange routing information. And this network will get added to routing interface, the routing table. So this will be the new routing table on router 1. We still have the directly connected client network. We still have the network to router 2. But now we have two 888 networks. One with the 24-bit net mask, learned through the link to router 2, and one with the 25-bit net mask, leading to the client network. Usually, routers look for the best match in the routing table to route traffic. So for the IP address 8888, it's going to look at this routing table and say, okay, I have these two networks in here, but the 25-bit net mask one is preferred because it's a better match. It's more precise, it's more specific, so that will be the one that I want to take. The routing table on router 2. It knows about the client network, learned through OSPF. It has the directly connected link to router 1. It has the directly connected 24-bit net mask to the 8 network. And it learned through OSPF the 25-bit net mask network of 888. This is really interesting. Router 2 has the 8888 address configured on one of its own interfaces. But still, if you do a trace route to router 8888, it goes to router 1 and to the hacker router, because of the more specific net mask. So even though it's a local address, it's going to send it out to one of its interfaces, away from itself. This basically means the hacker has now control of IP address 8888 for all sorts of DNS nasty things. There are a few mitigating measures. How to prevent this? You can make sure that every single OSPF packet gets a hash. MD5 has to make sure that the password you're configuring on all the routers in your domain match up, and unauthorized routers do not establish a neighbor relationship and are not able to inject false information into your network. Another one, you can configure OSPF links to be point-to-point, which means it only accepts a single neighbor. And the best one, if you're not going to be expecting a neighbor on a single interface, put it in passive. That basically means if you configure OSPF the way we did, with a large network statement of 0, 0, 0, everything, it means it's still going to advertise the network, but it's not going to establish a neighbor relationship over a specific network until you say it has to do it. If you say passive interval default, it will not try to establish a neighbor relationship over any of its interfaces. But it's going to be a good idea to allow it to build a neighbor relationship between router 1 and router 2. Another mitigating measures, we already discussed this, training. Make sure you, if you're managing a network, make sure you train, understand the protocols, understand the configuration, understand the consequences of your design, be able to make a proper design, being able to implement a proper design, verify a proper design, and manage it and troubleshoot it. And there's the logging. Like the previous one, if a new relationship is formed, it's going to show up in your logging. If you're going to be browsing through your logs on a daily basis, you're going to spot it. If you're sure that there was no failure and no planned maintenance and not anything, but you see a new neighbor relationship showing up, you need to take action. In short, this was a very, very brief overview of the spanning tree protocol and the OSPF protocol. This was not an in-depth one in protocol-wise. Are there any questions so far?
Niemand?
It's clear. Was sort of interesting. I know there's been quite a big call for next Hacker Hotel. Do you want more of this? I see a number of people. Good, I'll go talk to Dimitri. No questions. Well, here's the thing. I just showed you a few screens of, for example, the routing tables. I labbed all these scenarios out, and I brought the stuff with me. If anyone wants to see this in a real lab with real equipment, in the room below, I have this built out. If people want to see this, we can do a live demonstration.
But those companies use it.
Yes?
Why don't everyone use it?
These protocols or these...
Protocols and things to make it better.
These protocols are widely used. I'm a bit of a Cisco fanboy, and Cisco has a number of proprietary protocols, but the protocols I discussed here are open standards used by every vendor there is. So purposely discussed open standard protocols, so every vendor supports this and is able to run this. This is enterprise-grade networking users, spanning tree users, OSPF. There are other protocols possible, of course, but these two are widely used. In fact, within our own company, we use this as well. About securing them, not everyone has skilled staff, unfortunately. And I just showed you a few basic scenarios, again, for educational purposes only, for lab environments only, but these attacks do work. That's why I'm willing to lab them. I have to build a labs built below to show the configuration. Yes, it's there to let you see. Yes, it's possible to inject the router with or without adding the hacker devices. It really works this way. So this is not reconfiguring target devices. This is not affecting a target host. This is just manipulating the network in between to get hosts to do some certain stuff for you. So you don't touch the host, you don't touch the network, you just use the protocols what they were designed to do for. That's the best part of these network hacks. You're using existing protocols, you just let them work for you. Yes, we have a question.
You mentioned the talk, the Next Hacker Hotel. I'm sorry. You mentioned a talk at the Next Hacker Hotel. Is it within the scope of the work that you do to discuss the differences between, you mentioned Cisco, but the comparison between that and some of the controversy around the Huawei routers and DDWRT and whether to go with open source router firmware and what the relative advantages of going with each would be? It's a broad question, I know.
Basically, there's quite a big amount of politics involved in those discussions. I know, for example, I'm a Cisco fanboy, and I don't deny that, but I want to make this talk interesting for everyone, so I chose open standards. But every network vendor has its own pros and cons, and it usually gets to a level of either politics or fanboyism of other people. I know a couple of people who are vehement Juniper users, and I don't see that say that Juniper or Huawei is a bad network equipment. There is controversial in use. Talk of controversy. That's going to be a lot more politics and a lot less technical.
I guess I realize that everybody has suspicions about everybody else's home-built routers. Is there a more objective, arbitrary way to measure the relative security of these different types of companies' routers and the standards they use? And if you were to use that equipment, what steps could you do to help make sure your network was secure with them?
Well, that's a good question. I think there's multiple steps involved. First, you have the protocols. These can be vulnerable by design, but usually, especially when we're looking at things like encryption, there's also standards involved. But it's usually not the algorithm that's vulnerable, usually, but it's the implementation that's vulnerable. And a Cisco implementation of OSPF is going to be slightly different from a Juniper implementation of OSPF. It's going to be slightly different from Huawei implementation of OSPF. It's usually not the protocol that's vulnerable, it may be the implementation. And the security measures I showed here, they're part of the protocol and are basically implemented everywhere roughly the same. So I can make a workshop of how to secure these, but well, I just did the basics for both Spanning Tree and OSPF. I'm not sure I'm going to be able to fill an entire workshop on securing network protocols.
So in that regard, if given the crowd that you're addressing today, many people would be very amenable already to open standard type of router firmware and other things. Do you think that it would be appropriate for you to give an introduction to securing routers using DDWRT, for example? If it's out of the scope of what you do in your job, then that's okay. That's the basis of my question.
I don't know many enterprises who use DDWRT for their enterprise networks, but the securing part of the network of the protocols is part of the work I do, but securing specific implementations, that's going to make it less interesting very quickly for a larger group. And the group is not that big to begin with. It might have something to do with last night's pub quiz, but I'm not sure it's going to be interesting if I do a workshop on how to secure DDWRT. I can look into it, but.
Okay, thank you. I think my further questions can be addressed if you have the equipment downstairs. I'd love to see your demonstration.
Sure. Any other questions? No? And I would like to thank you all for attending and have an awesome day.